Just 4 light-years from Earth, our closest stellar neighbor, Alpha Centauri, holds a profound secret. A journey at the speed of light would cover this distance in less time than a standard university degree, making this system, in cosmic terms, a part of our immediate neighborhood. It was here, in August of 2024, that the James Webb Space Telescope aimed its golden mirrors and uncovered something entirely unexpected. The data pointed to a planet, a gas giant with a mass comparable to Saturn, circling the star Alpha Centauri A. Its orbit was measured at roughly twice the distance that separates the Earth from our own Sunday. This specific placement puts the world firmly inside what scientists refer to as the habitable zone, the region around a star where conditions could theoretically allow for the existence of liquid water. While a gas giant itself is not considered a candidate for life as we know it, any moons that might orbit such a planet could be far more hospitable. This scenario is reminiscent of the fictional moon Pandora from the film time's Avatar Asterisk, which was set in this very star system, creating a fascinating parallel between cinematic imagination and scientific discovery. The story, however, soon took a perplexing turn. When astronomers conducted follow-up observations in February of 2025, the planet had vanished. Another search in April of that year also came up empty. The world was simply gone. To understand this disappearance, scientists performed millions of computer simulations, which led them to a conclusion that was both elegant and startling. The planet had not disappeared at all. It had merely moved. Its orbit is not nearly circular like Earth's, but is instead highly stretched and elongated. There are times when the planet's path brings it extremely close to its star, where the overwhelming glare renders it invisible to Webb. At other times, its orbit carries it much farther out, allowing it to become visible once more. This orbital dynamic confirms the planet's existence, a conclusion bolstered by multiple observations from Webb and supported by archival data from ground-based telescopes dating as far back as 2019. If this discovery is fully verified, it would represent the nearest exoplanet ever to be directly imaged, the closest alien world we have ever seen with our own instruments. Furthermore, it exists in a location we could conceivably reach within a century, using propulsion technologies that are currently under development. But the planet's presence raises difficult questions. Alpha Centauri is a binary system, where 2 massive stars are locked in a gravitational embrace, orbiting one another every 80 years. For a planet to maintain a stable orbit in such a dynamically chaotic environment seems almost impossible. The immense gravitational forces should have either torn it to pieces or ejected it into deep space eons ago, and yet the evidence suggests it is there, waiting to swing back into our field of view. The research team is already arranging for more observation time, confident that the planet will reappear as its orbit brings it out from behind its star's light. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, may ultimately provide the definitive proof of what Webb has hinted at, a world next door, hiding in plain sight. And if a single planet can survive in such a turbulent system, one has to wonder what else might be concealed in the space between those twin suns. The answers to those questions may be closer than we imagine, but Webb's attention also had to pivot from the far reaches of space to a more immediate threat, an object discovered on a course toward us. On December 27, 2024, astronomers identified a rock tumbling through the solar system, giving it the designation 2024 YR4. Within weeks, it had captured the full attention of space agencies across the globe. The asteroid's size was estimated to be between 130 and 300 feet in diameter, making it comparable to a 15-story building. This may seem small when measured against the asteroid that struck Earth 66 million years ago, but an object of this size impacting a populated area would release an amount of energy equivalent to several nuclear bombs. Such an event would level a city, incinerate a wide radius, and send destructive shockwaves across an entire region. The central issue was its trajectory. Initial calculations revealed a small but tangible chance that this asteroid could collide with Earth on December 22, 2032. The odds, which started low, began to increase. At one point, the probability of an impact rose to nearly 3%. In the context of planetary defense, a 3% chance is considered a terrifyingly high risk. In a move that underscored the seriousness of the threat, NASA decided to point the James Webb Space Telescope at the asteroid. This was an extraordinary measure. Webb was engineered to study the faint light of the most distant galaxies, and its observation time is a precious commodity, meticulously scheduled years in advance. Yet, this powerful instrument was redirected to track a relatively small rock in our own solar system. The reason for this decision lies in Webb's ability to see in infrared light. By detecting heat, the telescope can help scientists determine an asteroid's true size with a precision that visible light observations cannot match. An asteroid's brightness in reflected sunlight depends on both its size and its surface reflectivity. A small, shiny asteroid can appear identical to a large, dark one, and this ambiguity complicated the early estimates. Was the object 130 feet across and highly reflective, or was it 300 feet wide and covered in dark, non-reflective material? The difference between these possibilities was critical for calculating the potential damage of an impact. Webb's observations in March of 2025 provided the needed answers. The data revealed the asteroid to be approximately 160 feet wide. While still large enough to cause regional devastation, this was significantly smaller than the worst-case scenarios. More importantly, continued tracking of the object refined its orbital path. By late February, NASA announced that the risk of impact had dropped to essentially zero. The rock, they confirmed, will miss us. But the incident exposed a disquieting reality. We almost missed it. The asteroid was discovered less than 8 years before its potential impact date. Had its trajectory been slightly different, or the odds of collision higher, 8 years might not have been enough time to successfully mount a deflection mission, and this is the scenario that keeps planetary defense experts awake at night. There are millions of asteroids in orbits that cross Earth's path, but we have catalogued only a tiny fraction of them. The next one might not come with an 8-year warning. It could be 8 months, or even 8 days. Webb has proven it can be an invaluable asset in these situations, but it cannot survey the entire sky. Something else is out there, moving through the darkness, still waiting to be found. While we often consider the danger of impacts from space, the telescope has unveiled a far more fundamental challenge to worlds once thought to be potential cradles for life. At a distance of 40 light-years from our own solar system, a small, dim red star emanates a steady, faint glow. In orbit around it are 7 planets, each comparable in size to Earth and composed of rock. The discovery of this system in 2017 sparked imaginations across the planet. It was named the TRAPPIST-1 system, a collection of 7 Earth-sized worlds. A remarkable feature was that 3 of these planets resided within the habitable zone, the region where conditions might allow for liquid water. For the very first time, humanity had located a place that seemed to possess the essential ingredients for life. But when Webb turned its powerful instruments toward this system, that hopeful vision began to disintegrate. The first world to be reassessed was the innermost planet, TRAPPIST-1b. Webb determined its temperature by observing the planet as it passed behind its star and then emerged again. The measurements revealed a scorched, airless surface, nothing more than bare rock being baked by unceasing radiation. Next came an examination of TRAPPIST-1c. The outcome was identical. No substantial atmosphere, no insulating layer of gases to shield it, just another lifeless world. The most significant disappointment, however, was yet to come. TRAPPIST-1d is positioned at the very inner edge of the habitable zone. This was a world upon which scientists had placed considerable hope. It absorbs an amount of energy from its star similar to what Earth receives from the Sunday. If any planet in this star system were to host liquid water, this was considered the prime candidate. In August of 2025, the research team published its conclusions. Webb's instruments had meticulously scanned for water vapor, methane, and carbon dioxide, the very molecules that constitute breathable atmospheres. The search yielded nothing. No telltale signatures, not even the faintest indication of their presence. The data pointed toward one of 3 possibilities for the planet. It might possess an atmosphere so thin that it would be comparable to that of Mars. Alternatively, it could be shrouded in clouds so dense that they prevent any form of detection. The third scenario was that it is simply a barren rock, completely devoid of any atmosphere. The lead scientist stated plainly that TRAPPIST-1d could be definitively removed from the list of worlds that might resemble Earth. This confirmation marked the end of another promising lead. The source of this planetary desolation appears to be the star itself. Red dwarfs such as TRAPPIST-1 are known for their volatility and violence. They are prone to unleashing powerful flares of radiation that far exceed anything produced by our own Sunday. These stellar outbursts bombard the nearby planets with enough energy to gradually erode their atmospheres over millions of years. The planets within the TRAPPIST-1 system orbit so closely that their years last only a few days in Earth time. They are effectively trapped within the high-energy blast zone of a stellar furnace. Yet, not all possibility is gone. The outer planets, designated E, F, G, and H, are situated farther away from the star. It is conceivable that they have managed to retain their atmospheric layers. Webb continues its observations, persistently searching for clues. For TRAPPIST-1e alone, an additional 15 observation sessions are planned. Preliminary data offers a tantalizing hint that this world might have a nitrogen-rich atmosphere containing traces of methane, reminiscent of Saturn's frozen moon, Titan. However, the current data is not yet conclusive. The star's violent eruptions interfere with the readings, making it a significant challenge to distinguish planetary signals from the background stellar noise. This work is pushing the very boundaries of what any telescope is capable of achieving. And as the search for signs of life on distant worlds continues, Webb has also brought to light a far more perplexing issue concerning the early universe: the existence of black holes that should not be there. The universe is 13.8 billion years old. In its initial moments, it was a uniform expanse of hot plasma and radiation. There were no stars, no galaxies, and no discernible structures of any kind. It was simply a roiling sea of particles expanding outward from the Big Bang. Over time, gravity began its slow, methodical work. Clumps of matter started to form, the first stars ignited, and galaxies began to take shape. At the core of these nascent galaxies, black holes were thought to have grown slowly and steadily. They would have fed on gas and dust over billions of years, eventually becoming the supermassive objects we see in the cosmos today. At least, that was the scenario predicted by established models. Webb's observations have fundamentally challenged those predictions. In November of 2025, astronomers reported the discovery of a supermassive black hole within a galaxy identified as CANUCSLRDZ86. While the name is technical, its implications are profound. This galaxy existed only 570 million years after the Big Bang. At that time, the universe was a mere 4% of its current age, still in its cosmic infancy. Yet, at the heart of this infant galaxy, a black hole was already consuming matter at a rate that defies conventional explanation. Its growth was far more rapid than any model permits, and faster than our understanding of physics suggests is possible. This finding is confirmed, has undergone peer review, and was published in Nature Communications. The ratio of the black hole's mass to that of its host galaxy contradicts every rule we thought we understood. In the modern universe, a typical supermassive black hole contains about 1/100th of 1% of its galaxy's total stellar mass. For every 10,000 units of mass in stars, the central black hole accounts for roughly 1 unit of mass. This ancient object, however, has a mass equivalent to 10% of its galaxy's total, a ratio 1,000 times higher than expected. The research team described the situation simply: the black hole is growing faster than the galaxy that contains it. This is not merely an isolated anomaly. Webb has identified hundreds of similar objects scattered throughout the early universe. Scientists refer to them as little red dots due to their compact size and reddish hue in infrared images. A great number of them seem to harbour rapidly accreting black holes enshrouded by hot gas and dust. So far, 70% of the little red dots that have been studied show evidence of active black hole feeding. Gas has been observed swirling at speeds greater than 2 million mph. Temperatures are high enough to ionize atoms, and the energy being emitted rivals that of entire galaxies. These objects present a direct challenge to our entire framework of cosmic evolution. There are a few possibilities. One is that black holes in the early universe were born much larger than we had assumed, perhaps collapsing directly from immense clouds of primordial gas. Another is that they discovered methods to feed at rates that should be physically impossible. A third possibility is that our fundamental models of the early universe are incorrect. The standard model of cosmology has been a reliable guide for science for decades. It had successfully passed every test it faced, until now. Something occurred in those first few 100 million years that we do not yet comprehend. Something that permitted these immense objects to form in the darkness before the first cosmic light had fully emerged. And these enormous entities were not the only unexpected discoveries. Webb found something else lurking in the ancient cosmos. Galaxies that seemed too large, too luminous, and to have appeared too soon. When Webb first directed its gaze toward the distant universe, astronomers anticipated seeing small, faint, and primitive galaxies. The early cosmos was expected to be a nursery of infant structures, small clusters of stars just beginning to coalesce. These were thought to be the building blocks that would later merge to create the grand spiral and elliptical galaxies we observe in the present day. The expectation was to find cosmic infants, but what the telescope revealed was something else entirely: giants. These were fully formed galaxies, each ablaze with the light of tens of billions of stars, already existing a mere 500 million years after the Big Bang. A few of them were so substantial they could rival the mass of our own Milky Way, a galaxy that required over 13 billion years to grow to its present scale. The discoveries prompted immediate, dramatic headlines, with some calling these objects universe breakers. They were described as being so massive and appearing so early that they seemed to defy the fundamental principles of cosmic evolution, sending scientists scrambling to find an answer. Our standard model of cosmology provides a roadmap for how the universe developed from the Big Bang until today. It details the way matter gradually clumped together through gravity, how dark matter created an invisible scaffold for galaxies to form upon, and the immense timescales these processes should follow. Based on this model, galaxies in the universe's youth were expected to be small. There simply should not have been sufficient time for them to accumulate so much mass, and yet, the observations showed them to be enormous and defiant. Some researchers began to wonder if the model itself was flawed. One possibility was that dark matter behaved differently in the primordial universe. Another was that the fundamental constants of physics might have shifted over time. The implications of such ideas were staggering, placing decades of established science in a precarious position. But the story soon took a surprising turn. Deeper analysis showed that many of these impossibly large galaxies were not quite what they appeared to be. While they were incredibly bright, that luminosity was not generated by stars alone. Concealed within their cores were actively feeding black holes. As gas spiraled into these gravitational wells, it produced tremendous amounts of heat and light, which made the host galaxies seem far more massive than they truly were. Once scientists adjusted their calculations to account for these black hole-powered objects, the crisis began to subside. The galaxies that remained were still larger than anticipated, but not impossibly so. The standard model, though tested, had survived. This conclusion was reinforced by a study published in 2024. The universe was not broken, but a significant mystery lingered. Even after compensating for the contamination from black holes, Webb continues to observe roughly twice the number of massive early galaxies that our models predict. Something about the primordial cosmos allowed stars to form with much greater speed than they do in the modern era. Perhaps the denser conditions of the time made it more difficult for stellar winds to disperse the necessary gas. It is also possible that the raw materials for star creation were simply more plentiful, or that early galaxies were just more efficient at converting gas into stars. Then, in early 2025, Webb presented another astonishing find: a massive spiral galaxy, nicknamed the Big Wheel, that existed less than 2 billion years after the Big Bang. Structures like spiral arms necessitate stability and require a great deal of time to settle into their graceful, rotating forms. Nevertheless, there it was, ancient and elegant, spinning in a way that contradicted all expectations. The early universe, it seems, was not the chaotic, disorganized place we had long imagined. It was a realm of structure, order, and maturity. And somewhere within that ancient darkness, new kinds of worlds were forming, worlds without stars and without light, destined to wander the void alone. There are trillions of them. Picture a planet adrift in space, bound to no star and receiving no warmth from above. It knows no sunrise and no sunset, only a continuous darkness stretching out in all directions. This is a frozen world, tumbling through the emptiness, completely untethered. These are known as rogue planets, and the James Webb Space Telescope has shown that they are remarkably common. In 2023, Webb identified 42 pairs of these wandering giants inside the Orion Nebula. Scientists named them Jupiter Mass Binary Objects, or JUMBOs. Each pair consists of two gas giants orbiting one another instead of a star, drifting through interstellar space like cosmic partners on an invisible stage. Finding so many was a complete surprise, and their formation was a profound puzzle. In 2024, Webb peered even deeper. Astronomers aimed the telescope at a young star-forming region named NGC 1333, located about 1,000 light-years from Earth. There, they discovered 6 more rogue planets, one of which was the lightest ever detected. It is a world with just 5 times the mass of Jupiter, and it is surrounded by a disk of dust and gas. The presence of that disk changes our understanding completely. Dust disks are the birthplaces of planets. Around ordinary stars, these disks coalesce into rocky worlds and gas giants over millions of years. But this rogue planet possesses its own disk, suggesting it could be forming a miniature planetary system of its own, perhaps with moons or even stranger objects. It would be a system of tiny worlds orbiting a frozen giant that, in turn, orbits nothing at all. This discovery implies that rogue planets are not only formed around stars and then ejected. It appears some may condense directly from clouds of gas in the same manner as stars. They are essentially failed stars objects that collected enough mass to collapse under their own gravity, but not quite enough to ignite nuclear fusion, and their population is immense. Theoretical models indicate that rogue planets may actually outnumber the stars in our galaxy, with estimates suggesting 2 trillion, or possibly even more. For every single point of light visible in the night sky, there could be multiple dark worlds drifting silently and invisibly in the cold space between them. In 2025, astronomers were able to detect one of these wanderers approximately 10,000 light-years away. They located it not by its own light, but by observing how it bent the light from a much more distant star, a phenomenon known as gravitational lensing. The rogue planet's mass created a warp in space-time itself, which acted as a natural magnifying glass. This particular world has about 70 times the mass of Earth, making it smaller than Saturn but larger than Neptune, and it drifts alone, unbound to any stellar system. The finding was confirmed through simultaneous observations from Earth and the Gaia Space Telescope. The most peculiar discovery, however, emerged in 2025 when Webb and the Very Large Telescope turned their attention to a rogue planet called Char Alpha 7. This frozen giant appears to be eating, devouring gas and dust at an incredible rate of 6 billion tons per second. It experiences accretion bursts that closely resemble the feeding behavior of young stars. Here is a planet that is acting like a star, growing, changing, and evolving in the darkness. We do not yet fully grasp what these objects are or what they could one day become. While these orphan worlds drift silently through the galaxy, Webb has also been observing something far more violent: stars on the verge of death. For decades, astronomers have been confronted with a persistent puzzle. When massive stars die, they explode as supernovae. The most prevalent type of massive star is the red supergiant, which are bloated, aging stars that have used up the fuel in their cores. According to theory, these stars should account for the majority of observed supernovae. Yet when scientists examined the historical records, red supergiants seem to explode very rarely. It was as if they were hiding. Then, on June 29, 2025, a supernova blazed into view in a galaxy 40 million light-years away. Astronomers designated it SN2025 PHT. As they searched back through archived images of that same region, they uncovered something that would solve a mystery that had spanned generations. The Webb telescope had already captured an image of this galaxy in 2024, building on observations Hubble had made as far back as 1994. By comparing these different views across time, scientists could pinpoint the exact star that had exploded. The star was confirmed to be a red supergiant, but the reason it had remained unseen for so long is what truly stands out. It was enveloped in a cocoon of dust so thick that it blocked nearly all visible light from escaping. In optical wavelengths, This cosmic shroud made the star appear more than 100 times dimmer than it actually was. For this reason, Hubble was unable to see it at all. Only the infrared vision of the Webb telescope could pierce that veil and finally reveal the dying giant hidden within. The star itself shone with the intensity of 100,000 of our own suns, but the surrounding dust concealed almost the entirety of that light. This makes it the dustiest, reddest supergiant progenitor ever observed prior to its detonation. The finding helps resolve a question that has persisted among astronomers for years. The universe's most massive stars are indeed exploding. They are simply cloaked in cosmic dust, making them invisible to instruments that only perceive visible light. The lead researcher conveyed that while his team had long argued that dust could be hiding these stars, even they did not anticipate discovering an example this extreme. Webb managed to capture the star in its final moments. The resulting images show a bloated, unstable giant teetering on the very edge of collapse, and then its core finally gave way. Gravity triumphed, and the star's outer layers were blasted outward at thousands of miles per second, leaving behind either a neutron star or a black hole. In July of 2025, Hubble captured the aftermath, a brilliant new point of light shining where the hidden star once lurked. The implications of this discovery are enormous. If the most massive stars in the cosmos are concealed behind dust, it means our entire census of stellar death has been incomplete. The rate of supernovae might be substantially higher than we have thought. The production of heavy elements, which are forged in these stellar explosions and then scattered across space, could be far more prolific than our calculations have shown. There is also one more unsettling detail. The closest red supergiant to our own planet is Betelgeuse, a massive, unstable star within the constellation Orion, which is visible to the naked eye on clear winter nights. Betelgeuse has been dimming and brightening in erratic patterns. Some scientists believe it could explode within the next 100,000 years, or perhaps even sooner. When it does, it will become a second star in our sky, bright enough to be seen in broad daylight. But before we witness that star's death, Webb revealed something even more peculiar: a planet that should not exist. It is shaped like a lemon and possesses an atmosphere that no one can currently explain. Only 1 million miles separate this bizarre world from the dead star it orbits. For perspective, Earth is situated 93 million miles from its own star. This planet orbits its host at roughly 1% of that distance. A single year on this world lasts less than 8 hours, and the gravitational pull is so intense that the entire planet has been stretched into an oblong, lemon-like shape. Scientists have given it the designation PSRJ 232 US 2650b, but the technical name is less important than what it represents. This world defies every established theory of planetary formation. Its host star is a pulsar, which is a type of neutron star, the collapsed core of a massive star that died in a supernova explosion long ago. Neutron stars are among the densest objects known to exist. A single teaspoon of their material would weigh billions of tons. This particular one spins with incredible speed, completing thousands of rotations every second and sweeping beams of radiation across space like a cosmic lighthouse. What is particularly fascinating is that the pulsar emits mostly gamma rays and high-energy particles, which are invisible to Webb's infrared detectors. This meant the telescope could observe the planet directly without being blinded by the light of a host star, providing a perfect, unobstructed view. What Webb saw caused researchers to pause. The planet's atmosphere is dominated by helium and carbon. There is no hydrogen, no water vapor, and none of the gases we would consider familiar. Instead, its skies are filled with clouds that resemble soot. Deep within the planet, under crushing pressures, that carbon might even be crystallizing into diamonds. The lead scientist described the finding bluntly, stating that this is a new type of planetary atmosphere that nobody has ever seen before. This was confirmed in a paper published in the Astrophysical Journal Letters in December of 2025. The mystery only deepens when one considers how this world could have formed. Normal planets coalesce from disks of gas and dust that surround young stars, but this planet orbits a stellar corpse. Did it somehow survive the supernova that created the pulsar? Could it have formed from the leftover debris, or did it wander in from another system and become captured? None of the standard explanations seem to fit the evidence. One theory proposes that the planet is actually the stripped-down remnant of a companion star. Pulsars sometimes exist in binary systems with other stars. Over billions of years, the pulsar can gravitationally steal material from its companion, gradually whittling it down to a tiny fraction of its original mass. It is possible this lemon-shaped world is all that remains of a star that lost 99.9% of itself. But even this scenario does not fully explain the carbon-rich atmosphere. Current models of nuclear physics do not account for the production of pure carbon in the quantities observed here. The researchers admit they may be looking at an entirely new class of object, something that falls between a planet and a stellar remnant, something for which we do not yet have a name. One scientist remarked that they did not expect this, and that it is extremely different from anything they had predicted. And somewhere else across the cosmos, Webb located another impossible world, a broiling hell planet covered in oceans of magma, wrapped in an atmosphere that should have been stripped away eons ago. The rules of planetary science just keep breaking. Located 280 light-years from Earth is a planet that orbits so close to its star that a single year lasts only 11 hours. This world is called TOI 561b, and its surface is a vast ocean of molten rock. Temperatures there exceed 3,000 degrees as lava churns beneath a hazy sky. According to every known principle of astrophysics, this planet should be a bare, airless rock. But it is not. In December of 2025, Webb detected something extraordinary. An atmosphere thick enough to redistribute heat from the planet's day side to its night side, and substantial enough to register clearly on the telescope's infrared instruments. This discovery should be impossible. Planets this close to their stars are relentlessly bombarded by radiation. The powerful stellar winds and ultraviolet light should have stripped away any atmosphere within a few million years. Yet TOI 561b still has one after more than 10 billion years of existence. The planet is ancient, one of the oldest rocky worlds ever discovered, having formed when the universe was less than half its current age. And somehow, despite all that time spent baking under the intense glare of its star, it managed to hold onto a blanket of gas. Researchers described it as a lava ball wrapped in air. This was confirmed by 37 hours of continuous observation using Webb's infrared spectrograph. The measurements revealed a dayside temperature that was far cooler than would be expected for a bare rock, providing clear evidence of an atmosphere at work. Without an atmosphere, the planet's temperature should have been close to 5,000 degrees, but the Webb telescope recorded a measurement of only about 3,000 degrees. The only viable explanation for this discrepancy is an atmosphere absorbing and then redistributing the heat. An intriguing question, however, is what kind of atmosphere could possibly survive in such extreme conditions? Scientists propose that the answer is found within the magma itself. As the rock remains in a molten state, it continually releases gases. Volatile compounds are thought to bubble up from the planet's interior, escaping to form a sky. Here on Earth, volcanic eruptions produce a similar effect, though on a profoundly smaller scale. On this hellish world, the entire surface is one vast volcanic ocean. This means the atmosphere is constantly being replenished from the planet below. In essence, the world breathes through its own lava. This particular discovery carries deep implications for the ongoing search for life. For a long time, astronomers have operated under the assumption that planets orbiting too near their stars could not possibly hold on to an atmosphere. Such worlds were typically dismissed as dead zones, not worthy of further investigation. Yet, if a planet can renew its atmosphere through its own geological activity, the traditional habitable zone might be considerably wider than we have previously imagined. This is not to suggest that TOI 561b is habitable in any way. Nothing could possibly survive on a world where the very ground is a sea of liquid fire, but the underlying principle could be applied elsewhere. It suggests that rocky planets with active interiors may be able to maintain their atmospheres in environments once thought to be completely inhospitable. The established rules are beginning to change. They shifted once more when Webb aimed its instruments at distant black holes, observing them not merely as they fed or grew, but as they were colliding and merging, sending ripples through the fabric of space-time itself. The most ancient black hole merger ever witnessed was waiting there in the primordial darkness. At 740 million years after the Big Bang, the universe was still in its youth. Galaxies were just beginning to form, and two supermassive black holes were spiraling toward one another, caught in a gravitational dance that would ultimately shake the structure of the cosmos. Webb managed to capture them in the middle of this process. The finding, which was announced in 2024, stands as the most remote black hole merger ever observed. It involved two galaxies crashing into each other, with two monstrous black holes at their cores circling ever closer, destined to become a single entity. This event was confirmed and published, its details verified through spectroscopic analysis that could separate the distinct light signatures of each individual black hole. One of the black holes contains the mass of 50 million of our suns. The other is believed to be of a comparable size, although it is buried so deeply within gas and dust that obtaining precise measurements has proven difficult. Eventually, they will combine into one supermassive black hole with a total mass equivalent to 100 million stars. This collision is expected to unleash gravitational waves, which are ripples in space-time that travel outward at the speed of light. The frequency of these particular waves is too low for current detectors like LIGO to register them. However, future observatories, such as the space-based LISA mission approved by the European Space Agency, will be capable of detecting mergers of this kind. The lead researcher on the study highlighted its significance, explaining that their work suggests mergers are a crucial pathway for the rapid growth of black holes, even at the dawn of cosmic time. But the implications of this discovery extend even further. The two galaxies involved in this merger are relatively small, with a stellar mass comparable to the Large Magellanic Cloud, a dwarf galaxy that orbits our own Milky Way. Despite their size, each of these galaxies contains a supermassive black hole that is larger than the one residing at the center of our own galaxy. By modern standards, this ratio is incorrect. Black holes are expected to be much smaller in comparison to their host galaxies. In the early universe, however, the balance appears to have been different. Black holes seem to have dominated, growing first while their host galaxies struggled to keep pace. The researcher added that, when considered alongside other Webb findings, their results demonstrate that massive black holes have been instrumental in shaping the evolution of galaxies from the very beginning. The merger also offers a glimpse into the violent nature of the early cosmos. Galaxies did not form in quiet isolation. Instead, they collided, merged, and tore one another apart, only to rebuild from the resulting wreckage. The supermassive black holes at their centers were not passive observers, but were active participants in this widespread chaos. When the two black holes in this system finally do merge, they will release more energy in the form of gravitational waves than all the stars in both galaxies combined. It will be a silent explosion, rippling across the universe at the speed of light. While we cannot see gravitational waves directly and can only infer their presence from their effects, Webb has provided us with the before image, showing the two black holes still distinct and spiraling toward their shared fate. And while black holes were colliding in the distant past, Webb uncovered something unsettling about the galaxies that formed around them. They were messy, turbulent, and struggling for survival. The Milky Way is a picture of order, a graceful spiral where stars orbit the galactic center along well-defined paths, tracing elegant arms that extend across 100,000 light-years of space. It took billions of years for our galaxy to achieve this stable structure, billions of years for the initial chaos of its formation to settle into the cosmic pinwheel we observe today. Webb looked back to a time before that calm had been established. In 2023, astronomers used the telescope to examine galaxies that existed between 400 and 600 million years after the Big Bang. They had anticipated finding young systems that were still in the process of organizing themselves. What they actually discovered was far more chaotic. The galaxies were messy, turbulent, and violent. Clouds of gas were not rotating in a smooth, orderly fashion. Instead, they churned with chaotic motions, slamming into one another at speeds that prevented any stable structure from forming. Stars were being created in sudden bursts rather than in a steady stream. The gravitational forces inside these galaxies were pulling in every direction simultaneously. One researcher described the situation quite simply, stating that these early galaxies struggled to settle down. The observations were made using a method known as grism spectroscopy, which enabled Webb to measure the movement of gas within these individual galaxies. The resulting data showed velocity dispersions that were much higher than those seen in modern galaxies. The gas was moving erratically, driven by powerful forces such as supernova explosions, black hole activity, and gravitational interactions with nearby systems. This represents the most detailed view yet of the galaxy formation process, a finding confirmed and published in the Times monthly notices of the Royal Astronomical Society *. These discoveries help explain a long-standing puzzle for astronomers. In Webb images, early galaxies frequently appear clumpy and irregular, with bright knots of star formation scattered across their surfaces in no discernible pattern. We now have a clearer understanding of why this is the case. The very gas from which those stars were forming was itself in a state of disorder. This turbulence prevented the formation of the smooth, rotating structures that would develop much later. But there is a more profound implication. If galaxies in the early universe were this chaotic, then the environments where planets were beginning to form must have been equally hostile. In the universe's infancy, stars that erupted into existence with great violence might have scattered their protoplanetary disks long before worlds had a chance to coalesce. Actively feeding black holes could have bathed entire cosmic neighborhoods in sterilizing radiation. Consequently, the sanctuaries where life might have taken hold were exceptionally scarce. Yet, even in this turbulent era, some galaxies achieved a state of order much sooner than anticipated. A spiral galaxy discovered in early 2025, given the nickname the Big Wheel, displays an elegant, rotating structure, even though it existed less than 2 billion years after the Big Bang. This particular galaxy seems to have somehow sidestepped the most intense periods of chaos. It is also possible that it developed a way to stabilize itself more rapidly than its cosmic neighbors. The early cosmos was far from uniform. Some areas were exceedingly violent, while others were comparatively stable. It was within these tranquil pockets that the necessary conditions for complexity could begin to emerge. The Webb telescope is helping us create a map that distinguishes between these different regions, but stability was not the sole prerequisite for complexity. Planets also required a form of protection, and Webb has revealed that for worlds around the galaxy's most common stars, such protection might be impossible to sustain. Red dwarfs are a ubiquitous presence. They account for roughly 70% of all stars in the Milky Way. These small, dim, and remarkably long-lived stars consume their fuel so gradually that they can continue to shine for trillions of years. If the evolution of life requires vast stretches of time, red dwarfs offer more of it than any other stellar type. There is, however, a significant problem. Red dwarfs are notoriously violent. They are known to unleash powerful flares of radiation with an unsettling frequency. These are bursts of ultraviolet light and charged particles that vastly exceed anything our own sun produces. Such flares are not isolated occurrences. They happen with great regularity, particularly in young red dwarfs. The planets that orbit these stars are positioned dangerously close to this zone of intense radiation. Because red dwarfs are so dim, their habitable zones are both narrow and nearby. For a planet to receive enough warmth to support liquid water, it must orbit within just a few million miles. At such a close proximity, stellar flares become a fundamental danger to their existence. Webb's observations of the TRAPPIST-1 system have highlighted this peril in stark detail. The 7 planets in orbit around TRAPPIST-1 are constantly immersed in radiation. The star itself is known for its volatility, emitting flares that have been documented by numerous observatories over many years. These energetic outbursts do more than just warm the planets. Over millions of years, they methodically strip away atmospheres, molecule by molecule. The innermost planets appear to have already lost whatever protective layers they may have once possessed. Observations of TRAPPIST-1b and c show no evidence of any substantial atmospheres. TRAPPIST-1d, which was once viewed as a leading candidate for habitability, seems to be similarly barren. The outer planets may have fared better, but only because they are situated farther from the most intense radiation. Yet distance by itself is not a guarantee of safety. Even TRAPPIST-1e, the most promising world within the system, confronts an uncertain future. Researchers who studied the planet discovered that the star's activity was corrupting their atmospheric data. Flares produce light at specific wavelengths that can imitate the signatures of planetary gases. Disentangling the star's light from any potential planetary signature is an extraordinarily challenging task. To address this interference, 15 additional observation sessions have been scheduled. Scientists plan to observe TRAPPIST-1e in conjunction with the inner planet TRAPPIST-1b, which is widely believed to be a bare rock. By comparing the data from both, they hope to subtract the star's contribution and thereby isolate any atmosphere that might exist on the outer world. If it turns out that TRAPPIST-1e has no atmosphere, the consequences would ripple far beyond this single system. Red dwarfs are the most prevalent type of star in our galaxy. If planets orbiting them are unable to hold onto their atmospheres, then the immense majority of potentially habitable worlds could be sterile zones. This would dramatically narrow the search for life, but the Webb telescope has not abandoned the effort. It continues to monitor red dwarf systems, looking for exceptions to the rule, seeking out worlds that have somehow endured the constant bombardment and searching for atmospheres that have refused to dissipate. And while some planets may be clinging to their air against incredible odds, others are being born in ways that no one had predicted, captured by Webb as a direct image inside a ring of debris in a cosmic first. For decades, astronomers located planets through indirect means. They observed stars as they wobbled from the gravitational pull of unseen companions. They recorded minute dips in starlight as planets passed in front of their host stars. They inferred the presence of worlds they could never actually see. The Webb telescope, however, changed that paradigm. In June of 2025, the telescope achieved something unprecedented. It captured a direct image of a newly forming planet inside the debris disk of a young star. The star in question is known as TWWA7, situated approximately 111 light-years from Earth. It is a cosmic youngster at only 6.4 million years old. It remains encircled by rings of gas and dust, the remnants of its own formation. These rings are precisely where planets are expected to take shape, and now, for the very first time, we have witnessed one in the process. The planet is located in a gap that separates the first and second rings of the debris disk. Its mass is estimated to be about 1/3 that of Jupiter. It follows an orbit 52 times farther from its star than Earth's distance from our Sunday. It is a cold, remote world, still in the process of gathering material from the surrounding dust. This finding has been confirmed and was published in the journal Times Nature Asterisk. The probability of this object being a background galaxy mistaken for a planet was calculated to be less than 1%. What makes this discovery so compelling are several distinct factors. First, it serves to validate a planet hunting technique that had been theorized for years. Gaps within debris disks have long been thought to be the home of planets. The gravity of a forming world is believed to clear out a path in the surrounding material, much like a snowplow carving through a fresh snowfall. The disk of TWWA7 has 3 separate rings, which suggests that multiple planets might be present. Webb has located one. Others could be found in the future. Second, this provides a unique snapshot of planetary formation as it happens. We are not observing a completed world, but rather watching its construction. The planet is still nestled within the disk that gave it life, possibly still accreting material and continuing to evolve. Third, it is a testament to Webb's extraordinary level of precision. To directly image a planet, one must block the overpowering glare of its parent star. The difference in brightness between a star and its planet is immense. Webb's coronagraphs, combined with advanced image processing techniques, made it possible to isolate this faint speck of light from the surrounding stellar noise. The research team had made a point of targeting young stars that could be observed from a polon perspective, which is like looking down on the system from above. This specific orientation offers an unobstructed view of the disk's structure and any planets that lie within it. TWWA7 will not be the last of its kind. Other young systems have already been scheduled for observation. The method has been proven effective, and so the hunt goes on. There is a certain poetic quality to this particular discovery. We are observing a planet taking shape around a star that is itself a mere infant in cosmic terms, witnessing creation as it happens. The universe is actively constructing new worlds before our very eyes. Yet, formation is just one part of the narrative. The Webb telescope has also documented an event at the very opposite end of a star's life, the most remote supernova ever witnessed. This was a star's final moments at the far reaches of the observable cosmos, taking place just 730 million years after the Big Bang. At this early stage, the universe was just beginning to emerge from its cosmic dark ages. The first stars had ignited their nuclear furnaces, and the earliest galaxies were starting to emit their faint light. Somewhere within that primordial glow, a star of immense mass underwent a catastrophic collapse. The resulting explosion, in a matter of seconds, unleashed more energy than our own sun will generate over its entire 10 billion year existence. A gamma ray burst shot outward at a velocity approaching the speed of light. Following in its wake, the supernova's expanding shell dispersed heavy elements forged deep within the dying star's core. Elements like iron, nickel, and cobalt, the essential ingredients for rocky planets, were scattered into the vast emptiness of space. 13 billion years later, the Webb telescope captured the lingering afterglow of this event. The sequence began on March 14th, 2025, when a space telescope known as SVOM detected an intense flash of gamma rays. Subsequent observations using the Very Large Telescope helped to confirm its immense distance. The light from this event had journeyed through space from a time when the universe was only 5% of its current age. Approximately 110 days after the initial burst, Webb directed its powerful infrared vision toward the source. The telescope produced images that successfully distinguished the fading light of the supernova from its host galaxy. The explosion remained visible, its glow still detectable even after billions of years of travel across an ever-expanding cosmos. This observation represents the most distant supernova ever to be confirmed, a finding published in Astronomy and Astrophysics in December of 2025. The discovery holds great significance because it forges a direct link between two phenomena that scientists had long suspected were connected. Gamma ray bursts are counted among the most powerful events known in the universe. While they have been observed for many decades, their precise origins have been a subject of debate. The prevailing theory suggested that long-duration gamma ray bursts were the product of collapsing massive stars. The supernova Webb observed provided the crucial piece of evidence. The supernova appeared in the exact same location as the gamma ray burst, sharing the same coordinates within the same host galaxy, confirming they were part of the same event. The massive star that generated the burst also exploded as a supernova, validating the long-held theory. But the story has more layers. The host galaxy itself is small and faint, one of the innumerable dwarf galaxies that populated the early cosmos. Within that tiny stellar system, a single, gigantic star lived its life and then died, seeding its local environment with the heavy elements that would one day contribute to new stars, new planets, and perhaps new life. We share a profound connection to cataclysms like this one. Every single atom of iron in our blood, every particle of calcium in our bones, was created in a stellar explosion billions of years in the past. The supernova that Webb saw is part of this grand lineage, a remote ancestor in our cosmic family tree, and the telescope continues its vigil, still scanning the ancient light for more explosions, more gamma ray bursts, and more clues about the violent processes that sculpted the universe we now call home. However, the early universe held yet another secret, something even more ancient than the first supernova: the echoes of the very first generation of stars. These are stars that may have, until now, remained entirely unseen. Before the first galaxies coalesced, and before the first supernovae scattered heavy elements across space, there existed a generation of stars that has never been observed. Scientists refer to them as population 3 stars. These were the firstborn stars, colossal giants composed of pure hydrogen and helium. These were the only elements available in the universe following the Big Bang. There was no carbon, no oxygen, and no metals of any kind. Only the simplest atoms in the cosmos, which collapsed under their own gravity until nuclear fusion ignited in their cores. Population 3 stars were massive on a scale that surpasses anything existing in the universe today, weighing hundreds of times more than our own star. They burned with incredible heat and brilliance, exhausting their nuclear fuel in only a few million years. They then exploded, seeding the cosmos with the very first heavy elements. Every atom heavier than helium that we see today can trace its origins back to these primordial giants. Yet, no one has ever directly witnessed one. They perished too long ago, and their light has been stretched and faded by 13 billion years of cosmic expansion. Webb, however, may have finally uncovered their fingerprints. In 2024, astronomers who were studying the galaxy GNZ 11 made an unexpected discovery in its outer halo. They found a cloud of gas containing no heavy elements whatsoever. It was pure hydrogen and helium pristine material, unchanged since the Big Bang. This cloud could very well be the birthplace of population 3 stars, the raw material from which that first generation would have formed. This finding is not yet a confirmation. Scientists are careful to state that they have not directly observed a population 3 star, but the existence of this pristine gas in the vicinity of such an ancient galaxy aligns perfectly with what theoretical models predict. The necessary ingredients are present, and the conditions appear to be right. GNZ 11 is one of the most distant galaxies ever seen, existing a mere 430 million years after the Big Bang. At its heart lies a supermassive black hole that is consuming matter at a tremendous rate. Yet on its periphery, untouched pockets of this primordial material have managed to survive. This is the closest humanity has ever come to observing the dawn of stellar creation. The significance of this goes far beyond simple curiosity. Population 3 stars are thought to have produced the first black holes through a process of direct collapse. They may have been the catalysts for the formation of the first galaxies by ionizing the gas around them. They were the engines that transformed the universe from a dark, uniform void into the structured and complex cosmos we see today. If Webb can locate more of these pristine gas clouds, scientists will be able to study the conditions that govern the formation of the first stars. They could test models of primordial nucleosynthesis and trace the chemical evolution of the universe from its simplest beginnings to the complexity of the present. The ghosts of that first light are still out there, concealed within the faintest signals from the most distant parts of space, and Webb is listening for them. But as the telescope looks deep into the ancient past, it has also brought to light something unsettling about our present. The universe is expanding, and it appears to be expanding more quickly than it ought to be. The universe is continuously getting larger. Every galaxy is moving away from every other galaxy. Space itself is stretching, carrying everything with it on this journey. This concept has been understood for almost a century. Edwin Hubble was the first to measure this expansion, back in the 1920s. Over the years, astronomers have painstakingly refined their measurements of the universe's expansion, a value known as the Hubble constant, which quantifies how rapidly the cosmos is stretching for a given unit of distance. A persistent problem, however, has emerged from this work. The results from different methods simply do not align. When scientists gauge the expansion rate using stars and galaxies in our local universe, they arrive at a value of approximately 73 kilometers per second per megaparsec. But a different approach, which calculates the expansion based on the cosmic microwave background, the ancient light left over from the Big Bang, yields a slower rate of roughly 67 kilometers per second per megaparsec. While the numerical difference appears small, it is far too significant to be dismissed as a simple measurement error. This suggests a fundamental flaw exists, either within the measurements themselves or, more profoundly, in our very understanding of the universe. This discrepancy, known as the Hubble tension, has been a source of deep concern in cosmology for more than a decade. The Webb telescope was intended to help settle the matter. In December of 2024, a team of researchers published the most extensive study of cosmic distances ever undertaken with Webb. Their work was remarkably thorough, employing 3 separate methods to measure the distances to galaxies that had hosted a supernova. The teams cross-checked all their findings and combined data from multiple, independent groups. The outcome was unambiguous. The measurements made by the Hubble Space Telescope were sound. The tension was not the result of instrument problems or errors in calibration. Webb had confirmed what Hubble's data had long suggested. The universe is expanding at a rate faster than the standard model of cosmology predicts. These findings were published in the Astrophysical Journal. This confirmation leaves us with 2 startling possibilities. The first is that some form of new physics is at work, accelerating the expansion in a way we have not yet grasped. The second is that the standard model of cosmology, which has been the bedrock of the science for decades, is fundamentally incomplete. The model already includes dark energy, the enigmatic force that pushes galaxies apart with increasing speed over time. But the existence of dark energy on its own is not enough to resolve the Hubble tension. Something else must be influencing the cosmos. Some theorists have proposed that dark energy might not be constant, behaving one way in the early universe and another way today. Others have put forward ideas about new particles or forces that were active only in the first few 100,000 years after the Big Bang. The potential explanations are as vast as they are unsettling. Adam Rees, the Nobel laureate who spearheaded the study, stated that the discrepancy suggests our comprehension of the universe may be incomplete. He received his prize for the discovery that the universe's expansion is accelerating. Now, he is faced with evidence that this discovery itself might not represent the complete picture. The Webb telescope has not solved the Hubble tension. It has made the problem more acute. The mystery has only deepened, and it seems that mysteries follow this observatory wherever it directs its gaze, including toward a familiar red giant star that could one day offer a celestial show for the ages. On a clear winter evening, one can look up and find the constellation of Orion. The hunter stands prominently in the southern sky, his belt of 3 stars easy to identify. A closer look at his shoulder reveals a star glowing with a noticeable reddish color, one that has fascinated humanity for centuries: Betelgeuse. It is among the largest stars that can be seen with the unaided eye. This red supergiant is so enormous that if it were placed where our Sun is, its surface would stretch beyond the orbit of Jupiter, and perhaps even beyond Saturn. The star is a bloated, unstable body approaching the end of its existence. It is a certainty that Betelgeuse will explode as a supernova. The only real question is when this will happen. In late 2019 and into early 2020, the star underwent a dramatic dimming. Over a period of weeks, its brightness fell to less than half of its usual level. This event sparked a wave of headlines questioning if Betelgeuse was about to detonate. Were we on the verge of witnessing the death of a star in our galactic neighborhood in real time? The answer, it turned out, was no. The dimming was the result of a cloud of dust that the star had ejected from its surface, which temporarily obscured its light. Betelgeuse was not dying, it was merely having a convulsion. This episode, however, served as a powerful illustration of just how unstable the star has become. Webb and other observatories have kept a close watch on Betelgeuse, monitoring its temperature, its luminosity, and the structure of its outer atmosphere. The collected data paints a picture of a star in turmoil. Its surface temperatures fluctuate, and it is actively casting off material into space. The star also pulsates, expanding and contracting over cycles that last for months. Some scientists believe that Webb has already found signs of accelerating instability. They point to changes in the star's infrared signature that could indicate its core is nearing the point of collapse. Yet making precise predictions is exceptionally difficult. In astronomical terms, the word imminent could mean tomorrow, or it could mean 100,000 years from now. What we do know is that when Betelgeuse does finally explode, the event will be nothing short of spectacular. The supernova will shine brighter than the full moon. It will even be visible during the daytime, a brilliant speck of light in the blue sky. For weeks, or possibly months, people on Earth will be able to watch a star die from a distance of 650 light-years. We will be perfectly safe. The star is too far away for the explosion to cause any harm to our planet. No lethal radiation will reach us, and no shockwave will disturb our atmosphere. We will simply have a front-row seat to one of the most powerful events the universe can produce. The heavy elements forged inside that stellar furnace will eventually spread through space, mingling with clouds of gas and dust. They will seed the next generation of stars and planets. It is possible that some of those very elements will one day become part of new worlds, and perhaps new life. We are, in a sense, stardust, observing stardust as it prepares to be scattered. And when that moment arrives, Webb will be watching too, capturing the death of a giant in unparalleled detail and adding another chapter to the story of how stars live and die. But this story does not conclude with death. It continues with creation. And Webb has discovered places where creation is happening now, on worlds that orbit no star at all. A planet without a central star was long thought to be a cosmic dead end. It would be a frozen ball of gas, drifting aimlessly through the void, unable to form anything more, unable to evolve, just a celestial orphan, living out eternity in the cold darkness between the stars. Webb has proven that this assumption was wrong. In July of 2025, astronomers released findings that challenged our core beliefs about planetary formation. Using Webb's highly sensitive infrared instruments, they examined 8 rogue planets with masses between 5 and 10 times that of Jupiter. These wandering giants float freely in space, untethered to any stellar system. For 6 of them, the telescope detected something extraordinary: extended infrared emissions that enveloped each world. It was the unmistakable signature of warm dust. These rogue planets possess debris disks. These are the same kinds of structures that are found around young stars, the same swirling rings of gas and dust out of which new planets are born. The remarkable difference here is that the central object is not a star, it is a planet. What stands out as even more striking is that the Webb telescope detected silicate grains inside these disks. Silicates are minerals, representing the fundamental material from which rocky worlds are made. Their existence here is an indication that dust is beginning to coalesce and crystallize, taking the very first steps toward the creation of solid objects. These massive, wandering planets may in fact be nurseries for miniature planetary systems of their own, a conclusion that was confirmed and published in the Astronomical Journal. The implications of this are simply staggering. Planetary formation, it seems, is not a phenomenon exclusive to stars. It appears that solitary, starless worlds drifting through the cosmos can assemble their own companions, which could be moons, or perhaps something more unusual. These would be tiny rocky bodies orbiting frozen giants that, in turn, orbit nothing at all. The lead researcher explained that the process of building planetary systems may not be limited to the environment around stars, but could also function around these isolated, sunless worlds. This discovery compels us to broaden our very definition of what a planetary system can be. Our imaginations have always placed planets in orbit around stars. Now, we are invited to envision planets orbiting other planets, creating systems within systems, like structures nested one inside another down to unknown scales. And our galaxy alone might harbor trillions of these objects. Rogue planets are exceptionally challenging to find because they produce almost no light of their own. They do not have a parent star whose glow they can reflect, nor do they pass in front of a stellar disk to cause a detectable transit. They remain invisible against the profound blackness of space, unless one knows precisely where to aim and possesses instruments with enough sensitivity to register their faint infrared heat signature. Webb is capable of seeing them, and it is discovering them in many places. The 6 rogue planets that were found to have debris disks were located in a young, star-forming region approximately 1,000 light-years from our own planet, but it is likely that similar objects are scattered throughout the galaxy in the vast expanses between the stars. We have only just started to map this hidden population, which may reside in the halos of galaxies and in the immense emptiness separating one stellar neighborhood from the next. If these rogue planets can indeed form their own moons, what other possibilities might they conceal? Could liquid water be present beneath the frozen surfaces of their companions, kept warm by tidal forces and the decay of radioactive elements? Could complex chemistry unfold in those dark oceans, shielded from the severe radiation of open space? The questions are accumulating far more quickly than the answers, but Webb also found something much closer to our own cosmic neighborhood. It captured a cold giant, lurking in our stellar backyard in a level of detail never before seen. A failed star drifts through the darkness just 12 light-years away from Earth. This object is called Epsilon Indi AB, and until not long ago, its presence was little more than a subtle gravitational hint, a pull on its parent star that suggested something massive was hiding nearby. Webb transformed that faint suggestion into a detailed portrait. In 2024, astronomers leveraged the telescope to directly image this object, which not only confirmed its existence but also revealed its characteristics with unprecedented clarity. Epsilon Indi AB is a gas giant with a mass roughly 6 times that of Jupiter. Its orbit around its star is at a distance comparable to that of Saturn's orbit around our Sun, and it ranks among the coldest exoplanets ever to be directly observed. Its surface temperatures linger at around 200 degrees below 0 Fahrenheit, a cold so intense it can freeze methane and condense exotic forms of ice that are not found on any world within our own solar system. This planet is a confirmed reality, visible and now under study. The significance of this discovery lies not only in the planet itself, but in what it signifies for the future of exoplanet science. The vast majority of exoplanets are identified through indirect means. We observe the gentle sway they cause in their host stars, or the slight dimming of starlight as they cross in front of them. Direct imaging, however, is different. It captures the actual light emitted or reflected by the planet. These are photons that have journeyed from that remote world all the way to Webb's mirrors, providing a true picture of an alien atmosphere. Epsilon Indi AB is near enough and cold enough that Webb was able to analyze its composition. The resulting data points to an atmosphere with high concentrations of methane and possibly ammonia, bearing some resemblance to Jupiter and Saturn but being significantly colder, older, and more evolved. For billions of years, the planet has been gradually cooling, slowly releasing the heat from its formation into the void of space. And this is where the story becomes particularly interesting. The star that Epsilon Indi AB orbits is itself quite remarkable. Epsilon Indi A is a K-type star which is slightly smaller and cooler than our Sunday. It is a member of a triple system that also includes two brown dwarfs failed stars that never managed to ignite fusion within their cores. The planetary architecture of this system is therefore highly complex, with multiple bodies of different masses all gravitationally bound, influencing one another's orbits over eons. By observing Epsilon Indi AB, scientists can gain insights into planetary evolution that our own solar system cannot offer. While Jupiter and Saturn are about 4.5 billion years old, Epsilon Indi AB may be even more ancient. It offers a look at a more advanced stage in the aging process of a giant planet. What happens to atmospheres over such immense timescales? How do clouds form and then dissipate? How does internal heat find its way out through layers of exotic gas? Webb is beginning to provide answers to these questions, and those answers will deepen our understanding of giant planets everywhere, including those that might host moons with liquid water. These could be moons where life might theoretically emerge, even in orbit around cold, ancient worlds far from the warmth of any star. But warmth is not always a prerequisite. As Webb has shown, sometimes heat can originate from very unexpected places. When we imagine a habitable world, we tend to picture a place like Earth, a rocky planet bathed in the light of a yellow star and enveloped in a protective atmosphere. Yet Webb has begun to reveal that habitability might manifest in forms we had never considered. Deep within frozen worlds, heat can be retained for billions of years. The source of this warmth is not starlight, nor is it proximity to a stellar furnace. It is something far more subtle. One source is radioactive decay, the slow breakdown of unstable atoms buried deep in a planet's core, which releases energy particle by particle and warms the interior from within. Another is tidal forces, the gravitational stretching and squeezing that happens when a moon orbits closely to a massive planet. This constant flexing generates friction, and friction, in turn, generates heat in some cases, enough heat to sustain liquid water beneath a thick shell of ice. This is not merely a theoretical concept. We can see evidence of it in our own solar system. Europa, one of Jupiter's moons, possesses a global ocean beneath its frozen crust. Enceladus, a moon of Saturn, expels geysers of water vapor into space. Both of these worlds are warmed not by the sun, but by their own internal processes. And both are now regarded as among the most promising locations in the search for life beyond Earth. The James Webb Space Telescope has been observing these distant moons, measuring their surfaces, studying their compositions, and searching for indications of geological activity. What the telescope's data suggests is that the conditions necessary for subsurface oceans may not be a rarity. In fact, they could be quite common throughout the galaxy. Even rogue planets with large moons might harbour similar environments, frozen on their exteriors, but warm and wet underneath. These hidden realms would be cut off from any starlight, sustained instead by the slow decay of radioactive elements and the unending pull of gravity. Life in such a place would be alien in ways we can scarcely comprehend. There would be no photosynthesis and no connection to the energy cycles of a star, only chemistry unfolding in perpetual darkness, powered by the planet's own internal heat. Scientists have a name for this process: chemosynthesis. On Earth, it takes place in the deepest oceanic trenches, where hydrothermal vents discharge mineral-rich water into the abyss. Entire ecosystems manage to thrive there, wholly independent of light, including tube worms, blind shrimp, and bacteria that metabolize sulfur instead of oxygen. If this kind of life can exist on our world, it stands to reason it could exist on others. Webb cannot detect life directly, as no telescope is capable of such a feat. It can, however, identify the conditions that make life possible, such as liquid water, sources of chemical energy, and stable environments over geological time. The telescope has located these very conditions in places we never anticipated, around rogue planets, within debris disks, and on frozen moons that orbit far-off giants. The quest for life is no longer restricted to the conventional habitable zones around stars. It has now broadened to encompass the dark voids between them, the frozen wanderers, and the hidden oceans. The universe is proving to be larger and more peculiar than we ever thought, and Webb is only just beginning its exploration. Yet not all of its discoveries evoke a sense of wonder. Some bring a feeling of unease, like the growing awareness that the cosmic neighborhood we believed we understood is filled with objects we have only started to catalogue. We have charted the stars, compiled lists of galaxies, and mapped the structure of the cosmic web across billions of light years. Still, there is a class of objects that has mostly evaded our surveys: brown dwarfs. These celestial bodies are essentially failed stars. They are objects that formed from collapsing clouds of gas, just as stars do, but they never accumulated enough mass to ignite hydrogen fusion within their cores. They emit a faint glow from the residual heat of their formation before gradually cooling and fading into darkness over billions of years. Webb has now revealed that brown dwarfs are significantly more numerous than we had realized, and they are also far more varied. In December of 2025, the telescope captured images of a young star cluster named Westerlund 2, located approximately 20,000 light-years from Earth. Concealed among the brilliant young stars, Webb discovered a population of brown dwarfs with masses as low as 10 times that of Jupiter. These are some of the lightest free-floating objects ever detected that were created through the process of stellar formation. Their existence blurs the line that separates planets from stars. They are too large to have formed inside a planetary disk, yet too small to sustain fusion. They are something in between. It has been confirmed that the cluster holds roughly 3,000 stars and an unknown quantity of these transitional objects. This discovery presents a challenge to our classification systems. What should we call an object that forms like a star but possesses the mass of a planet? Is it a star that failed or a planet that succeeded? The distinction is important because it influences how we count the objects in our galaxy, how we calculate the total mass of matter, and how we model the evolution of stellar populations. And brown dwarfs are not the only hidden population. Webb has identified objects that are even smaller. These are rogue planets with masses only a few times that of Jupiter, drifting through star-forming regions without any companion star. They are objects that may have been ejected from their original planetary systems, or perhaps collapsed directly from gas clouds before they had a chance to grow larger. The galaxy is crowded with these invisible wanderers. Conventional surveys that use visible light fail to see most of them. Brown dwarfs are simply too cool and too faint. Rogue planets are even more difficult to spot. Only infrared telescopes like Webb are capable of detecting their dim thermal signatures against the cold backdrop of space. The implications of this are significant. Dark matter is the unseen scaffolding that holds galaxies together, and its true nature remains one of the greatest puzzles in physics. Some scientists have proposed that brown dwarfs and rogue planets might make up a portion of this missing mass. The numbers do not seem to fully resolve the issue. Brown dwarfs and rogue planets combined cannot account for all of dark matter, but they do contribute to it. We just did not know by how much until Webb started counting them. This invisible census is now underway. Each new observation adds more entries, cataloguing new objects that were always there, lurking in the darkness, simply waiting to be found. But some of Webb's discoveries are not merely surprising. They are also sobering reminders that the universe functions on scales of time and space that dwarf human comprehension. Carbon is found everywhere in the cosmos. It is forged in the cores of dying stars and then scattered across space by supernova explosions. It serves as the backbone of organic chemistry and the foundation of life as we know it. Under the right conditions, it can also transform into something extraordinary: diamonds. Webb has found evidence suggesting that diamond formation may be occurring inside alien worlds, not as rare gemstones buried in rock, but as entire layers of crystallized carbon deep within planetary interiors. The lemon-shaped planet orbiting a pulsar, which was discovered in 2025, provides the clearest example yet. Its atmosphere is dominated by carbon. Clouds that resemble soot drift through its helium-rich skies. And beneath that atmosphere, the pressures build to levels that would crush any material found on Earth. Under such immense pressure, carbon does not stay as soot, it crystallizes. Its atoms lock into the rigid lattice structure of a diamond. Layer builds upon layer over billions of years. Scientists cannot look inside this planet directly. They can, however, model what happens when carbon-rich atmospheres are situated above dense interiors. The physics involved is well understood. At a sufficient pressure and temperature, the formation of diamonds is inevitable. It is possible this planet has a core made of diamond. While this is not confirmed through direct observation, it is consistent with all the data Webb has measured, including the atmospheric composition, the extreme pressures implied by the planet's proximity to its pulsar host, and the spectral signatures of carbon in its various forms. And this particular planet is not unique. Theoretical models indicate that diamond-rich interiors could exist in many worlds across the galaxy, particularly in gas giants that have enough carbon in their atmospheres. The universe Webb reveals is one where our earthly chemistry is far from the norm, a place filled with exotic possibilities. We can envision super-Earths with such extreme internal pressures that their geology is utterly alien, or even rogue planets that originally formed from carbon-rich materials. The implications of such compositions extend well beyond simple geology. The interesting detail is that diamonds are remarkably efficient at conducting heat. A planet with a substantial diamond layer in its interior would therefore have a completely different thermal profile, affecting how warmth travels from the core to the surface. This, in turn, would shape its volcanic activity, the evolution of its atmosphere, and perhaps even the conditions for habitability on any moons that might orbit such a world. We are only just starting to grasp the strange and wonderful chemistry that governs these distant planets. The Webb telescope has shown us that the cosmos is not built from the familiar substances we find here on Earth. Instead, it is a realm of extremes. Here, pressures can compress atoms into entirely new arrangements. Temperatures can liquefy rock and turn metal into vapor, and environments exist where the ordinary becomes truly extraordinary. Carbon serves as just one compelling example. It is likely that other elements behave in equally unexpected ways under these alien conditions. We see hints of this in the metallic hydrogen thought to exist in the cores of gas giants, the superionic water ice within the mantles of ice giants, and the exotic alloys formed under pressures we are incapable of replicating in any laboratory on Earth. Webb provides a crucial window into these extreme environments. While it cannot physically visit these worlds or drill into their cores, it possesses the ability to measure their atmospheres, infer their chemical makeup, and construct models of what lies hidden beneath their surfaces. And what lies beneath is proving to be far stranger than we ever could have imagined. Yet, strangeness is not the only narrative woven into Webb's discoveries. There is also beauty, tragedy, and the slow, inevitable march of cosmic time. 13 billion years in the past, a galaxy died. It did not perish in a spectacular explosion or a cataclysmic collision with another system. It simply stopped forming stars. The raw material needed for new stellar births was either used up or driven away, and the galaxy fell silent. While its existing stars continued to burn, no new ones were ignited to take their place. In 2024, Webb located this cosmic relic, a dead galaxy from a time when the universe itself was barely 700 million years old. This discovery represents the youngest galactic graveyard ever found. According to our understanding, this should not have occurred so rapidly. Galaxies are expected to form stars continuously over billions of years. Our own Milky Way is still producing new stars today, approximately 4.5 billion years after it first formed. Star formation is the very pulse of a galaxy. When it ceases, the galaxy is, for all cosmic purposes, dead. But this ancient galaxy had already flatlined when the universe was just 5% of its current age. Scientists refer to such objects as quiescent galaxies. They are not uncommon in the modern universe, as elliptical galaxies, for instance, often exhibit very little ongoing star formation. The challenge, however, is finding one so early in cosmic history, which puts our models of galactic evolution to the test. Something must have shut down its star formation with brutal efficiency. The most probable culprit is the supermassive black hole at the galaxy's heart. As these black holes consume matter, they unleash tremendous amounts of energy. Powerful jets of radiation and superheated gas blast outward, heating and expelling the cold gas that would otherwise collapse to form new stars. This process, known as feedback, can effectively sterilize a galaxy in a remarkably short period. Webb's observations lend support to this theory. The dead galaxy exhibits signs of having once hosted an active black hole. It is plausible that this black hole consumed so much material so quickly that it annihilated the very conditions necessary for continued star formation. In a way, the galaxy was choked by its own insatiable appetite. This finding, confirmed and published in the journal Nature in 2024, reveals something profound about the relationship between black holes and their host galaxies. They are not merely passive residents, they actively shape one another. Black holes can nurture galaxies by stirring up gas and triggering bursts of star creation, or they can murder them by blowing that essential gas away. This delicate balance between creation and destruction has played out across all of cosmic history. Some galaxies manage to thrive, while others die young. Webb is now cataloguing these different outcomes, counting the living and the dead, and mapping the vast cosmic graveyard that extends across billions of light years. In doing so, it is teaching us about the potential fate of our own galaxy. The Milky Way has a supermassive black hole at its center, one that is relatively quiet at present, but has fed in the past and will certainly feed again. In 4 billion years, our galaxy is set to collide with Andromeda. This merger will send vast streams of gas spiraling toward both of the central black holes. What will happen then is uncertain. Will it be an act of creation or one of destruction? The answer may already be written in the faint light of those ancient dead galaxies. The Andromeda galaxy is falling toward us. It is 2.5 million light-years away, but that distance is steadily shrinking. In roughly 4 billion years, it will collide with the Milky Way. The two spiral galaxies will merge, their stars scattered into new orbits, and their central black holes will eventually combine to form a single, supermassive monster. This is not a speculative theory. It is a conclusion confirmed by decades of observation. The motion of Andromeda relative to our galaxy has been measured with extraordinary precision, making the collision an inevitability. Webb has shown us what such collisions look like as they happen in real time. Across the distant universe, the telescope has captured galaxies in various stages of merging. We see spirals twisted into chaotic forms, long streams of stars torn from their parent systems, and brilliant bursts of star formation ignited by the compression of gas clouds. At their centers, the black holes draw ever closer, preparing for their own powerful union. These images serve as a preview of our own distant future. The merger itself will not destroy Earth. The spaces between stars are so immense that direct collisions are exceedingly rare. Our planet will likely survive the event, perhaps cast into a new orbit around the newly merged galactic core. The night sky will transform, and our familiar constellations will dissolve, but the world itself is expected to endure. What Webb has revealed, however, is that these mergers are not gentle events. The gravitational chaos unleashes waves of star formation as gas clouds collapse under the strain of powerful tidal forces. Supernova rates spike as massive, short-lived stars are born and die in quick succession. Entire regions of space are bathed in intense radiation. Moreover, the central black holes do not merge quietly. As they spiral together, they emit gravitational waves, which are ripples in the very fabric of space-time. Their final coalescence releases more energy in a single moment than all the stars in both galaxies combined, an immense and silent thunderclap echoing across the cosmos. Future gravitational wave detectors will one day be able to sense mergers like the one that awaits our galaxy. But that technology is still decades or even centuries away. For now, we can only observe the aftermath of distant collisions and imagine what our descendants might one day witness. Webb has also shown that these galactic mergers are a crucial mechanism for seeding the cosmos with heavy elements. When galaxies collide, the event sparks the formation of immense stars, which burn brightly but for only a short time. As they die in supernova explosions, they disperse elements like iron, gold, and uranium, everything heavier than the primordial hydrogen and helium. The future merger with Andromeda will infuse our combined galaxy with this newly forged material. From this enriched gas, new generations of stars will ignite. The planets that form around them will integrate these heavy elements into their very structure, from their cores to their crusts. This cosmic impact, in a profound way, represents an inseparable dance of creation, destruction, and ultimate rebirth. While the Webb telescope cannot peer into the future, it offers a clear window into the distant past. Looking back through time, it has revealed innumerable instances of galaxies merging, transforming, and evolving. What becomes clear is that the universe is far from static. It is a system of perpetual renewal. And within this grand, dynamic process, our own significance seems smaller than we ever conceived. On a cosmic scale, a distance of 40 light-years is almost negligible, a mere rounding error in the vastness of the galaxy, a short stroll across the interstellar void. Yet, within this relatively small bubble of space, the Webb telescope identified 7 planets, the size of Earth, orbiting a single star. These were worlds that once held great promise as potential abodes for life, but they have since been largely dismissed. TRAPPIST-1b was found to be a scorched, airless rock. TRAPPIST-1c revealed a similar story. For TRAPPIST-1d, no atmosphere resembling Earth's could be detected. While the system's outer planets are still being examined, a concerning pattern has emerged. The most promising nearby worlds we have identified are being systematically disqualified. This is the story of just one star system. Our very closest stellar neighbor, Alpha Centauri, might host a giant planet, but gas giants are not considered conducive to life as we understand it, and any potential moons they may have are entirely speculative. The closest verified exoplanet around a single star similar to the Sun is Barnard's star B, located about 6 light-years from us. Its calculated mass and orbit point to a frozen world, situated well beyond its star's habitable zone. Webb has discovered thousands of exoplanets throughout the galaxy, but a frustrating reality persists. Those near enough for detailed study appear inhospitable, while those that could be habitable lie too far away for our current instruments to analyze in depth. The resulting silence from the cosmos is profound. For more than 60 years, humanity has been listening for signals from other civilizations. Radio telescopes have methodically scanned the heavens for engineered transmissions, and optical surveys have searched for signs of laser communications. The result has been absolute quiet, without a single verified detection of intelligent life. Some scientists maintain that our search has only just commenced. They point to the immense size of the galaxy and the limitations of our technology, suggesting we have explored only a minuscule fraction of the cosmic haystack. Others propose that the silence hints at a more sobering reality. It could be that intelligent life is exceedingly rare, or that it typically self-destructs before achieving interstellar reach. Or perhaps the requirements for complex biology are so uniquely precise that our own planet is a statistical anomaly. The Webb telescope cannot provide direct answers to these existential questions. Its mission is not to find life itself. However, each world it observes contributes a vital piece of data to the overall puzzle. Every atmosphere it scrutinizes either strengthens or weakens the idea that habitable environments are common. To date, the information gathered is ambiguous. We have confirmed that rocky planets are plentiful throughout the galaxy. The challenging detail is that rocky worlds with stable atmospheres orbiting within the habitable zones of calm stars seem to be uncommon. The cosmos is teeming with planets, but it appears the majority of them are lifeless. This conclusion does not necessarily mean that we are alone. It simply implies that the quest is more challenging than we once anticipated. It also suggests that if life does exist on other worlds, it could be separated from us by distances we can never traverse, by spans of time we cannot imagine, and by chasms of empty space that render communication futile. We are incredibly small, and the universe is immeasurably large. Yet we continue to search, to hope, and to aim our instruments toward the darkness, listening for a reply. In just over 3 years of operation, the James Webb Space Telescope has already transformed our understanding of the cosmos. It has forced the revision of textbooks, overturned long-held assumptions, and unveiled a universe far more strange and intricate than we had ever envisioned. Its observations have included black holes that grew to impossible sizes too quickly, galaxies that appeared far too early in cosmic history, and planets that defy our models of formation. It has found atmospheres that puzzle scientists and even rogue worlds, creating their own planetary systems in the cold darkness between stars. A common theme runs through every one of these revelations. Our own place in the universe is more modest than we realized. The cosmos does not center itself on Earth. It is indifferent to human timelines and concerns, functioning instead according to physical laws that play out over billions of years and across distances so great that even light takes eons to travel them. Webb has given us an unparalleled view of our immediate cosmic vicinity. At Alpha Centauri, only 4 light-years from us, there may be a giant planet whose existence was previously unknown. We see asteroids crossing our own orbital path, often with little time to track their trajectories. The stars that glitter in our night sky are frequently violent and unstable, bathing their surroundings in radiation that would render any nearby planet sterile. Yet, the telescope has also revealed profound beauty. It has captured images of nebulae, illuminated by the glow of infant stars. We have seen galaxies tracing elegant spirals through the void, and watched planets coalescing within rings of cosmic dust. These are the very same mechanisms that constructed our own world 4.5 billion years ago. The cycles of creation and destruction, of life and death, repeat themselves throughout the cosmos on a scale that truly humbles the mind. And somewhere within all that immensity, we find our home. We reside on a small, rocky planet that circles an average star tucked away in an ordinary spiral galaxy. We are one world out of trillions, one species among an unknown number that might be scattered throughout the observable universe. While Webb cannot answer whether we are alone, it can sharpen our focus on what to search for. It helps us identify atmospheres with the correct chemical signatures, planets in the proper orbits, and stars stable enough to allow life a chance to emerge. The quest goes on. Each new observation contributes another piece to this grand puzzle, refining our knowledge of what is possible and what is not. The universe is not hostile toward us, it is simply indifferent. Yet within that very indifference, there is space for hope. Life emerged on Earth, which means it could potentially arise on other worlds. The necessary conditions for it exist, and the raw ingredients are distributed throughout every galaxy Webb has studied. Whether we will ever detect another intelligent species in the cosmic silence is a question that remains unanswered. But we have moved beyond simple speculation in the dark. We are now actively observing, measuring, and learning. The James Webb Space Telescope is more than just an instrument. It serves as a mirror, reflecting our own cosmic insignificance as well as our vast potential. It shows us our origins and provides clues about where we might be headed. This great exploration has only just started, and by witnessing these discoveries, you have become a part of that journey. Every question that arises, every spark of curiosity, every glance toward the night sky links you to the fundamental human drive that conceived of this telescope and aimed it toward the distant stars. It has been said that we are the universe observing itself, and the Webb telescope is granting us a clearer view. The conventional understanding of supermassive black holes is that they remain fixed. They are the gravitational anchors at the centers of galaxies, held in place by the collective pull of billions of stars. There they sit, slowly drawing in matter and growing over cosmic timescales. They are not supposed to move, nor are they meant to escape, and yet, sometimes they do. Near the end of 2025, Webb confirmed a phenomenon that had been suspected for many years. A supermassive black hole was speeding through the cosmos at more than 2 million miles per hour. It was not merely drifting or oscillating, it was fleeing. This object was first identified by the Hubble Space Telescope, which saw it as a peculiar streak of light trailing from a galaxy in the distant universe. Initially, researchers speculated that it could be an instrument artifact, perhaps a cosmic ray impacting the detector, or simply a glitch. The streak, however, was still present in all follow-up observations. The truth finally came into focus when Webb aimed its infrared sensors at the source. A supermassive black hole had been forcibly ejected from its parent galaxy, thrown out by gravitational dynamics so intense that they overwhelmed the binding force of hundreds of billions of stars. The physical mechanism behind such an event is known as a three-body interaction. When two galaxies merge, their central black holes will eventually begin to spiral toward one another. If a third black hole is introduced into this system, the gravitational situation becomes profoundly chaotic. One of the three can be flung away at an immense speed, while the other two coalesce. This is what was determined to have happened, a conclusion supported by spectroscopic analysis, which showed the runaway's velocity matched the predictions of computer simulations. Yet the luminous trail left behind the black hole is not merely scattered debris. It is a stream of stars, new suns being born in the object's wake as it plows through the rarefied gas of intergalactic space. As the black hole passes, it compresses this gas, and that compression is sufficient to trigger gravitational collapse. Stars ignite, forming a trail that spans over 200,000 light-years, a cosmic contrail that marks a path of both destruction and creation. Nothing of this nature has ever been witnessed before. The implications of this are quite profound. If supermassive black holes can be ejected from galaxies, it means the universe is home to wandering giants that we have never factored into our cosmic census. They are invisible behemoths, drifting through the voids between stellar archipelagos. These are black holes with no galaxy to call their own, no stable orbit, and no predictable path. We have no way of knowing how many are out there. Detecting a runaway black hole is only possible if it happens to be interacting with surrounding matter. Should it travel through empty space, it leaves no signature. The one Webb discovered was an accidental finding, a product of a lucky alignment and a chance observation. There could be thousands more, perhaps millions, silently threading their way through the cosmic web at speeds that defy comprehension. This leads to a sobering thought. Our own Milky Way galaxy is on a collision course with Andromeda, set to merge in roughly 4 billion years. Both galaxies host supermassive black holes. If that future merger unfolds in a particular way, it is possible one of those black holes, including our own, could be ejected. The cosmic neighborhood appears to be more hazardous than we had ever imagined, but danger is not always a distant phenomenon. At times, it can be found in familiar places, like the giant planet in our own solar system, where Webb has seen weather systems that reflect the most peculiar storms on Earth. Saturn's largest moon, Titan, is one of the most enigmatic worlds in our solar system. It has a substantial atmosphere, denser than that of Earth. It has lakes and seas, rivers and rain. The critical distinction is that the liquid is methane, not water. Hydrocarbon oceans meet frozen shorelines beneath a hazy, orange sky. Webb has been studying Titan, and its discoveries are altering our perspective on this strange world. In 2024, the telescope captured the first conclusive evidence of cloud convection in Titan's northern hemisphere. It observed methane clouds forming, rising, and creating storms that drop hydrocarbon rain onto the surface below. This is weather alien in its composition, but weather nonetheless. The same essential physics that power thunderstorms on Earth are operating on a moon where temperatures are near negative 290 degrees Fahrenheit. The discovery was accomplished by combining Webb's observations with data gathered by the Keck telescope in Hawaii. Together, they allowed scientists to track cloud formations moving across Titan's disk, watching them evolve over hours in a manner that aligned perfectly with what meteorological models had predicted. The result was confirmed and published by an international team that studies the dynamics of Titan's atmosphere. The detail that makes this so significant is that the northern hemisphere of Titan is where most of the moon's lakes and seas are concentrated. The methane cycle on Titan acts as a mirror to the water cycle on Earth. Liquid evaporates from the surface, ascends into the atmosphere, condenses to form clouds, and then falls back down as rain. That rain feeds rivers that have carved channels into the frozen ground and which ultimately drain into the hydrocarbon seas. Webb has now observed this entire process in action for the first time from its orbit around Earth. The implications of this reach far beyond Titan itself. If complex weather can operate on a frozen moon almost 1 billion miles from our planet, then similar processes could be occurring on countless worlds across the galaxy. This could include exomoons orbiting giant planets in distant systems, or even rogue planets possessing thick atmospheres and internal heat. Any world with the proper mix of temperature, pressure, and volatile compounds could have weather. It is not a uniquely terrestrial phenomenon, but a universal one that simply uses different chemical vocabularies throughout the cosmos. And Titan offers us something more, a laboratory for exploring prebiotic chemistry. The hydrocarbon molecules raining down from Titan's atmosphere are the same kinds of building blocks that may have led to the emergence of life on a young Earth. Methane, ethane, and more complex organic molecules collect in lakes where chemical reactions can play out over billions of years. No one is making the claim that Titan hosts life. The temperatures are far too low for liquid water, and without liquid water, life as we know it cannot exist. But the chemistry is there. The raw materials are in abundance. The processes are actively unfolding. Webb will continue to monitor Titan as the seasons on that distant moon slowly change. A single Titan year is 29 Earth years long, and the northern summer is just now commencing. The storms may become more powerful, the rains may become heavier, and we will be watching. But Titan isn't the only familiar world where Webb has uncovered surprises. Closer still, the largest planet in our solar system was exhibiting a display unlike any previously recorded. Jupiter is a world of superlatives. It is the most massive planet in our solar system, with the fastest rotation turning on its axis in just 10 hours. It possesses the strongest magnetic field of any planet, 20,000 times more powerful than our own, and it is home to the most violent auroras ever seen. In 2024, Webb turned its instruments toward Jupiter and captured something extraordinary. At Jupiter's poles, the auroras were not merely glowing spectacles. They were vibrant, erupting displays of energy, their patterns and intensity shifting with each passing minute. On Earth, auroras are born from the solar wind's charged particles interacting with our planet's magnetic shield, resulting in a gentle, shimmering dance. Jupiter's auroral phenomena, however, exist on an entirely different magnitude. The particles that cascade into its atmosphere possess vastly more energy. Their origin is not just the solar wind, but also the volcanic moon Io, which continuously ejects about 1 ton of sulfur and other materials into space every second. This ejected matter becomes ensnared by Jupiter's immense magnetic field, where it is accelerated to incredible velocities and funneled down toward the polar regions. The resulting light show makes our own northern light seem like a flickering candle next to a raging wildfire. Webb's unique infrared capabilities allowed it to perceive details hidden from other instruments, such as temperature fluctuations within the auroral zones and the chemical fingerprints of molecules being shattered and reformed by the particle onslaught. It even mapped the three-dimensional architecture of the magnetic field lines that channel this energy into the atmosphere. The data held an unexpected discovery. The auroras were changing far more rapidly than existing models had predicted. Luminous spots would materialize and then disappear within moments, and entire sections would flare up and then fade, as if the planet's magnetic field were experiencing a momentary disruption. Researchers are still working to understand the full implications of these observations. One potential explanation is that the interplay between Jupiter and Io is significantly more dynamic than previously thought. An alternative theory suggests that processes occurring deep inside Jupiter's atmosphere influence how this auroral energy is distributed. Whatever the cause, these findings underscore how even celestial bodies studied for centuries retain the capacity to surprise us. And the telescope's revelations at Jupiter didn't end there. High above the Great Red Spot, the legendary storm that has churned for at least 3 centuries, Webb identified atmospheric characteristics that had never been seen. It discerned layers of haze and unusual chemical signatures, suggesting the storm's influence extends much farther into the upper atmosphere than ground-based observatories could ever resolve. Jupiter is far from a static object. It is a world in constant evolution. Its massive storms drift and combine, and its auroras pulse with a rhythm we are only now beginning to comprehend. Webb is slated to continue its observations of this giant planet, compiling a long-term, time-lapse record of its atmospheric dynamics. Over the coming years and decades, new patterns may become clear, and the fundamental physics that govern this enormous world might finally be brought into sharp focus. But Jupiter, for all its mysteries, is at least a familiar neighbor. Webb has also detected objects of a much stranger origin, visitors from beyond our solar system, briefly passing through on their immense journeys across the galaxy. In late 2024, astronomers identified something that did not belong in our cosmic neighborhood. It was a comet, but it was not one of our own. Its journey began in interstellar space. This object received the designation 32, Atlas, making it just the third confirmed interstellar visitor ever recorded. The first was the elongated, cigar-shaped object known as Oumuamua, which appeared in 2017 and prompted a great deal of speculation before it disappeared back into the outer solar system. The second, Comet Borisov, arrived in 2019 with a more conventional cometary appearance, confirming that such interstellar objects were not a singular event. 3.2. Atlas, arriving in 2024, immediately became a target for every major observatory, including Webb. The Space Telescope turned its instruments toward the comet in August of 2025 during its closest approach to our star, and its findings were remarkable. In many ways, the object acted just like a familiar comet. It displayed a coma, the hazy cloud of gas and dust that envelops a comet's core. It also had jets, which are streams of material that erupt from the surface as ice sublimates in the relative warmth of the inner solar system. It even sported a tail, though a faint one, streaming behind it as it sped through our region of space. The crucial difference, however, was its composition, which was distinctly alien. Spectroscopic analysis uncovered chemical fingerprints unlike those of comets that formed alongside Earth. The specific ratios of certain elements and compounds indicated that this object had coalesced billions of years ago around a distant star within a planetary system with very different environmental conditions. We were, in essence, examining a piece of another solar system, a fragment of a world that might have been cast out into the void to wander for eons before chance guided it into our view. Webb's observations, combined with data from the Hubble Space Telescope and observatories on the ground, helped paint a complete picture of this visitor. The comet is now departing, falling back toward the interstellar darkness, on a path that will never bring it back. Within a few years, it will have grown too dim for even our most powerful telescopes to see. Its journey will continue through the galaxy, perhaps passing near other stars or simply drifting through the dark for eternity. Yet its brief passage has taught us something profound. Interstellar objects are not a rarity. They likely pass through our solar system with some regularity. We simply lack the sophisticated instruments to find them until very recently. One can only wonder how many have come and gone unnoticed, while humanity was still discovering fire. The galaxy is filled with this kind of debris, the scattered leftovers of planet formation, now wandering between the stars. It is conceivable that some of this material could carry complex organic molecules, the very building blocks of life, drifting on cosmic currents and potentially seeding new worlds wherever they might land. Webb cannot track every interstellar traveler, but it can study those we do find, and each one offers a unique story about a faraway solar system we can never otherwise visit. This reveals that the universe is connected in ways we are just beginning to grasp. Galaxies themselves do not drift in isolation. Instead, they are linked by immense filaments of gas and dark matter that stretch across hundreds of millions of light years. This grand structure is known as the cosmic web, and Webb is now unveiling it in unprecedented detail. Imagine the universe not as a random scattering of points, but as a vast, sponge-like structure. Galaxies tend to cluster along the surfaces and intersections of this cosmic sponge, concentrated in filaments and nodes. In between these structures lie enormous voids, regions of space that are almost entirely empty. This intricate architecture took shape in the first few 100 million years following the Big Bang. Infinitesimally small variations in the density of primordial matter were gradually amplified by gravity over cosmic timescales. The denser regions attracted more material, growing even denser, while the sparser regions became emptier as their matter was pulled toward the growing filaments. Webb has now managed to image portions of this cosmic web directly. In 2024, the telescope gathered light from distant quasars, which are the intensely brilliant cores of active galaxies fueled by supermassive black holes. As this light traveled across the cosmos toward Earth, it passed through the intergalactic medium. The diffuse gas residing between galaxies absorbed specific wavelengths of the quasar's light, leaving behind a distinct pattern of fingerprints within the light spectrum. By analyzing these unique spectral fingerprints, astronomers were able to create a map showing how gas was distributed all along the path of the light. What emerged from the data was a picture of immense, sprawling filaments of hydrogen that stretched between entire galaxies, occupying the very locations that cosmic web simulations had long predicted. This finding served as a powerful confirmation of the theory, making the invisible scaffolding of the universe visible for the first time across these vast cosmic distances. Yet, the Webb telescope also uncovered something that was not anticipated. Certain filaments appeared to contain a much greater volume of gas than the models had suggested, while others held significantly less. The distribution was not smooth and uniform as simulations had indicated, but rather clumpy and uneven, revealing a far more complex structure. This discovery is profoundly important because the cosmic web is the mechanism that governs how galaxies are able to grow. Gas, the raw fuel for star formation, travels along these filaments and is funneled into the galactic nodes. If the supply lines themselves are uneven, it follows that the growth of galaxies must also be uneven. Some galactic systems are fortunate to receive a plentiful supply of fuel, allowing for robust star creation, while others are effectively starved of resources. These new observations are compelling theorists to go back and revise their foundational models of the universe. The cosmos, it seems, is a messier and more chaotic place than we had previously assumed, and its evolution is less predictable. Furthermore, the cosmic web is not a static structure. It is a dynamic entity that evolves over immense timescales. Filaments can merge and combine, while the great voids between them continue to expand. Galaxies themselves migrate along these gravitational currents, drawn inexorably toward the densest concentrations of matter. Our own galaxy, the Milky Way, resides within a relatively modest node of this grand cosmic structure. The local filament that we inhabit connects our galactic neighborhood to the Virgo cluster, a massive collection of over 1,000 galaxies located approximately 50 million light-years from Earth. We are currently falling toward the Virgo cluster, pulled by its immense gravity, participating in a cosmic flow that has been unfolding for billions of years. The Webb telescope cannot observe our local segment of the cosmic web directly, simply because we are embedded deep within it. However, by carefully studying these distant structures, we can begin to infer what our own cosmic neighborhood might look like from an outside perspective. We are but a single strand in an infinite tapestry, a solitary thread in a web that spans the entirety of the observable universe. And somewhere within that web, concealed in the profound darkness between the filaments, lies the very substance that holds the entire structure together. It is the enduring mystery that has so far refused to be solved: dark matter. A staggering 85% of all matter in the cosmos is completely invisible. This elusive substance neither emits nor absorbs light, and its only known interaction with ordinary matter is through the persistent pull of gravity. We are unable to see it, touch it, or directly detect it with any instrument humanity has ever constructed. And yet, without its gravitational influence, galaxies would simply fly apart. Stars would never have had the chance to form. The cosmic web itself would not exist. Everything we can observe in the universe depends on something that remains fundamentally unobservable. While the Webb telescope was not specifically designed to study dark matter directly, a task no telescope can perform, it possesses the unique ability to observe the effects of dark matter with a level of precision that has never before been possible. And so far, these observations are serving to deepen the mystery rather than provide a clear solution. The key technique used for this work is known as gravitational lensing. When light from a very distant galaxy travels past a massive object, its path is bent by gravity. This massive object effectively acts as a cosmic lens, which both distorts and magnifies the light from the background source. The precise degree of this bending allows astronomers to calculate the total mass of the lensing object, including both its visible matter and its unseen dark matter. Webb has now studied dozens of these gravitational lensing systems. In every single case, the halo of dark matter that surrounds the lensing galaxy has proven to be far more massive than all of its visible stars and gas combined. The ratio is remarkably consistent with our cosmological predictions, showing about 6 times more dark matter than ordinary matter, a result confirmed across numerous independent observations. The dark matter is unquestionably there, but the fundamental question remains: what is it? For several decades, the leading hypothesis has proposed that dark matter is composed of undiscovered particles. These hypothetical particles, known as WIMPs, or weakly interacting massive particles, would have formed in the early universe, and have been drifting silently through space ever since. For more than 30 years, sophisticated experiments on Earth have been searching for any sign of these particles. To date, nothing has been found. Other hypotheses continue to be explored. These include axions, which are theoretical particles even lighter and more elusive than WIMPs, as well as primordial black holes that might have formed in the first chaotic moments after the Big Bang. Some theories even suggest that our understanding of gravity is incomplete, proposing modifications to the laws of physics that would eliminate the need for dark matter entirely. Webb's observations cannot directly distinguish between these competing possibilities, but they can place important constraints on the options. If dark matter behaves in specific ways, it should leave detectable signatures in the large-scale distribution of galaxies and in the fine structure of gravitational lenses. Thus far, the data has been frustratingly consistent with the simplest of models: cold dark matter that moves slowly, clumps together under its own gravity, and forms vast halos around galaxies, behaving exactly as predicted. The mystery endures. Whatever dark matter ultimately proves to be, it is the architect of the universe we inhabit. It was the force that determined where galaxies would first form. It controlled the flow of primordial gas along the cosmic web. It created the deep gravitational wells where stars could ignite and planets could coalesce. Our very existence is owed to something we cannot see, and every new observation that Webb makes adds another constraint, another crucial data point, another piece to a cosmic puzzle that may take many more decades to finally solve. The universe holds its secrets close. But Webb has found the places where new secrets are being written, in the regions where stars are being born and planetary systems are just beginning to take shape. These are the nurseries of creation. Stars are not born in isolation. They emerge from within vast, cold clouds of gas and dust, molecular nurseries that can span dozens of light years across. Inside these clouds, gravity relentlessly pulls material together, forming dense cores that eventually collapse and heat up until nuclear fusion ignites at their center. The Webb telescope has peered deep into these stellar nurseries with a clarity that no previous telescope could ever achieve. It has turned its gaze to iconic regions of star formation that have been photographed for decades, such as the Carina Nebula, the Eagle Nebula, and the Orion Nebula. But all previous images of these objects showed only the surfaces of the clouds, revealing just the outer layers, illuminated by bright, nearby stars. Webb, however, sees right through them. Its ability to detect infrared light allows it to bypass the dense dust that blocks visible wavelengths. For the very first time, we are able to observe the hidden interiors of these star-forming regions, witnessing the dense cores where protostars are still gathering mass, the powerful jets of material being blasted from young stellar objects, and the swirling disks of gas and dust where planets are just starting to form. In 2022, Webb released its first breathtaking images of the Carina Nebula. The level of detail was simply staggering. The images revealed majestic pillars of gas being sculpted by intense radiation from hot, young stars. They uncovered hundreds of previously unseen protostars, still embedded deep within the cloud, and they showed clear evidence of star formation proceeding in successive waves, likely triggered by the expansion of earlier stellar generations. As these observations have continued, however, they have revealed something quite surprising. It appears that star formation is more efficient than we had previously realized. Existing models predicted that only a small percentage of a molecular cloud's total mass would ever be converted into stars. The rest, it was thought, would be blown away by powerful stellar winds and radiation before it had a chance to collapse. But Webb's observations are showing higher conversion rates in some of these regions, with more stars forming and more of the available mass being utilized. It is quite possible that the early universe operated in much the same way. A compelling explanation for why Webb observes so many enormous galaxies at high redshift is that star formation was simply more prolific in the distant past. Surveys of numerous star-forming regions have confirmed that the primordial raw material was converted into stars at a much faster rate than contemporary theories had accounted for, prompting a rewriting of the physics governing stellar birth. And deep within these stellar nurseries, Webb has uncovered something else entirely: the very first stages of the formation of planetary systems. Many young stars are encircled by protoplanetary disks, which are vast rings composed of gas and dust that will in time coalesce to create planets, moons, comets, and asteroids. Webb has produced images of these disks with an unprecedented level of detail, showing gaps where planets might already be taking shape, spiral arms generated by gravitational instabilities, and chemical gradients that dictate the kinds of worlds that can ultimately emerge. One particular disk, surrounding a star only a few 100,000 years old, revealed signs of water ice at distances where rocky planets could form, suggesting the building blocks for habitable worlds are present from the earliest moments of stellar evolution. Across the galaxy, creation is unfolding in this very moment as new solar systems begin to form. It is possible that some of these may one day harbor life, and we are witnessing this process as it happens. Not all stellar systems, however, are straightforward. Some are significantly more intricate and perilous. Most stars in the galaxy do not exist in isolation, but instead have companions. Binary systems, in which two stars orbit a common center of gravity, are actually more prevalent than solitary stars like our own Sunday. Triple and even quadruple systems can also be found, indicating that the stellar population is inherently social. This complexity presents a serious problem for planets. Within a binary system, the gravitational forces are extraordinarily complex, forcing a planet to secure a stable orbit, either very close to one star or far enough away to circle both. An improper orbit inevitably leads to chaos, as gravitational tugs from the two stars can stretch orbits, heighten their eccentricity, and ultimately either eject a planet into deep space or send it spiraling into one of its parent stars. Webb has found planets that have managed to survive in these hostile environments, and their very existence challenges our models. The candidate planet near Alpha Centauri A offers a prime example. Alpha Centauri is a binary system, with its two stars completing an orbit of each other every 80 years. The prospective planet circles one of these stars at a distance where it should be subject to intense gravitational perturbations from the companion star, yet it seems to have endured for billions of years. Other binary systems present similarly surprising findings. Webb has imaged debris disks around binary stars, which indicates that the formation of planets is possible even within gravitationally complicated settings, and some of these disks display gaps where worlds may already reside. Then, in 2025, astronomers reported the discovery of a planet orbiting a star within a system containing not two, but three stellar members. This hierarchical triple system consists of a close binary, orbited by a third, more distant star, and the planet circles that distant star, far enough from the inner pair to preserve its stability. This discovery, confirmed and published in peer-reviewed journals, shows that planets can indeed form and persist in systems once thought to be far too chaotic. The implications for habitability are profound. Binary and multiple star systems were frequently disregarded as unlikely places to find life due to the gravitational turmoil, variable radiation, and unstable orbits, all of which seem to prevent the long-term stability that life requires. But if planets can survive in these systems, then the number of potentially habitable worlds in the galaxy expands dramatically. Given that binary stars are so common, if even a small fraction of them host stable planets, the galactic census of possible homes for life grows by billions. While Webb cannot directly ascertain habitability, it can pinpoint where planets exist, map their orbits, and determine if conditions might allow for liquid water. Every new discovery enriches the catalogue, which is growing more rapidly than anyone had anticipated. Worlds have been found around single stars, binary stars, pulsars, and brown dwarfs, and even as rogue planets, revealing a staggering diversity of environments where they can emerge. The universe demonstrates more creativity than our theories ever conceived, but that creativity is not without its limits, as some environments are simply too extreme for anything familiar to exist. Webb has identified worlds that push these limits to their breaking point. One such planet is HD 189733b, a world where it rains glass sideways. It orbits so near its star that one hemisphere is permanently locked, facing the inferno, with dayside temperatures that climb beyond 2,000 degrees. Silicate rock vaporizes, ascends into the atmosphere, and is then swept by supersonic winds toward the night side, where it condenses and precipitates as molten glass. Webb has studied this world, measuring its temperature fluctuations and mapping the zones between its eternal day and perpetual night. It is a hellscape beyond our imagination, and it is not alone. The exoplanet category, known as hot Jupiters, has presented one extreme after another. These are gas giants orbiting so close to their stars that they complete a full year in fewer than 2 Earth days. They are worlds where iron vaporizes on the day side only to rain down on the night side, and their atmospheres exhibit temperature inversions, where upper layers are hotter than the layers below, a behavior that defies that of any planet in our own solar system. Webb's spectroscopic instruments have provided a window into these alien atmospheres, reading the chemical fingerprints of distant skies across light years of space. These analyses have detected water vapor, carbon dioxide, methane, and sulfur dioxide, but the chemistry is often strange. Some hot Jupiters show signs of clouds composed of corundum, the same mineral that forms rubies and sapphires. Others possess atmospheres thick with titanium oxide, a compound we use on Earth in sunscreen. The chemical combinations are exotic, the conditions are severe, and the environments are utterly alien to our experience. Yet these worlds are real, their existence confirmed through transit observations, radial velocity measurements, and now direct spectroscopy from Webb. Their presence raises a fundamental question. If the universe can create worlds as bizarre as these, what else might be out there? Perhaps there are rocky planets with surfaces of pure diamond, formed from carbon-rich mantles crushed under immense pressure. There might be ocean worlds completely enveloped in water hundreds of miles deep, with no solid ground at all, or carbon planets where graphite and carbides take the place of the silicate rocks common to Earth. Webb has already found hints of some of these exotic compositions, including a super-Earth with an atmosphere that suggests a surface of molten magma, and a Neptune-like world with an unusual carbon-to-oxygen ratio. The data remains fragmentary, but the implications are vast. We had once assumed that planets would generally resemble the worlds within our own solar system, with perhaps only minor differences. We are familiar with the planetary categories of our own solar system, the rocky worlds like Earth and Mars, the gas giants such as Jupiter and Saturn, and the ice giants, Uranus and Neptune. The universe, however, had other ideas. Each new observation unveils a broader spectrum of possibilities, revealing novel combinations of mass, composition, and orbital paths. These new environments challenge our fundamental definitions of what a planet can be. The Webb telescope is expanding our cosmic vocabulary, teaching us new words for worlds we never imagined. And somewhere within that expanded lexicon, there may be a word for a planet like Earth, a place where life could take hold. The search goes on. In 1990, the Voyager 1 spacecraft, from a distance of nearly 4 billion miles, turned its camera back toward home. The image it captured revealed our planet as just a tiny speck, a fraction of a pixel suspended in a beam of scattered sunlight. Carl Sagan called this view the pale blue dot. He observed that the entirety of the human experience, every person ever known and every civilization that has ever existed, unfolded on that mote of dust. Webb has not imaged Earth, and for safety reasons, it cannot. The telescope must point away from our region of space to avoid being damaged by the brightness of objects so close to it. But in its place, it has achieved something perhaps more profound. It has shown us what Earth might look like from the outside. By studying exoplanets in distant star systems, Webb is revealing the kinds of signatures a living world might produce. These are the chemical fingerprints of life, an atmosphere containing oxygen, the presence of methane that should not persist without being constantly replenished by biology, and water vapor and carbon dioxide in just the right proportions. Earth exhibits all of these signatures. If an alien civilization pointed an instrument like Webb at our solar system, they could detect our presence. What they would see is a rocky planet in the habitable zone of a stable star, wrapped in an atmosphere that practically screams of biological activity. We are detectable, a visible data point in someone else's survey. This realization changes the search for life itself. It means the very techniques we are now developing to find biosignatures on exoplanets could be used by others to find us. The universe may already know we are here, or it may not. The distances are vast, and the signals are incredibly faint. Even Webb, the most powerful space telescope ever constructed, can only study the atmospheres of a handful of nearby worlds in detail. An equivalent telescope located in another galaxy would see nothing of Earth at all. We find ourselves in a strange position, visible but small, detectable but obscure, one world among trillions. Webb has placed Earth in its proper context, not as the center of the universe, but as one example of what is possible, a template for habitability that may or may not be replicated elsewhere. The search for other Earths continues. Webb has already identified promising candidates, which are rocky planets in habitable zones with the right sizes and orbits. But confirming that any of them actually hosts life will require technology far beyond what currently exists. Future telescopes may be able to accomplish what Webb cannot, such as the direct imaging of exoplanet surfaces or spectroscopic analysis sensitive enough to detect trace biosignatures. In time, missions to nearby systems could study alien worlds up close. This journey will take decades, perhaps centuries, but it has begun. Every discovery Webb makes adds to our understanding of where life might arise, where it could thrive, and where we fit in the cosmic story. We are the pale blue dot, small and fragile, but we are also the species that built this telescope and pointed it toward the stars. That, in itself, is not nothing.